Our next speaker, we're very fortunate to have him here in the US. David Fallon is from ING Belgium, and ING has been very active in evaluating and using in-memory computing technologies for quite a few use cases, both to improve their business, as Abe just talked about with digital transformation, and also to respond to regulatory requirements, which are continually increasing in across the globe. David is an IT enthusiast with more than 15 years of experience developing distributed applications, mainly in Java. His broad international experience covers telecom, retail, and mainly financial institutions. The last 10 years, he has been engineering solutions for the highly demanding banking environment. David has been pioneering the work on Ignite and GridGain since its introduction in ING Belgium more than 2 years ago. And please welcome David Fallon to the podium.
Hi, thanks for having me. It's really an honor to speak again. And thanks for Abe for the digital transformation introduction. I think it's a good introduction to what I'm going to present on how ING is going through its own digital transformation. I'll first start with a story. 20 years ago, when I was a student, I got this summer job where I work in a bank at the cashier's desk. I remember those people line up, and they had the booklets with all operations that happened on their accounts. So they would line, they would queue, and give me their booklets. I would enter some operation on the computer, put the booklet in this dot matrix printer. You know, this. Remember this sound? It really makes me. I remember this sound. It's really nice. And so I will print out the statements, and they will have their account balance, and I will give them back the booklet, and they will look back happy or not, depending on their balances, but they will walk out of the branch. So if you think about it, it took them so they had to go out of home, to walk or drive to the bank, wait in line, give me the booklet. I was very efficient, so I could do it very quickly. And then after, let's say, half an hour, they would have the balance. I mean, who would accept that now? Everyone in this room, I'm sure, can check the balance in less than a minute. I mean, those were not the good old days. Well, unfortunately, the systems that were running then, well, they're still running now. So that's the legacy of a systemic bank. The ING is more than 40 years old. It's a main bank in Belgium and in the Netherlands. And all these basic banking services are still running on mainframes. For instance, customer information, which is the base of all operations, is running on mainframe. Payment systems still run on mainframe. So all these systems that were running 20 years ago, when I was working then, are still running in mainframe. I would say big thumbs for those people who coded the systems 20 years ago, because I don't know if the code I've wrote now is it will still be running in 20 years. It's kind of impressive when you think about it. One of the issues as well is that those mainframes, well, they're used by many applications in the bank. So we have a lot of dependencies also on those mainframes. And the migration out of those mainframes is very complex. Well, first, they do a tremendous job. They're still working very fast. They're very powerful computers. But yeah, this link that we have with those mainframes is very complex to break. The issue is, Internet mobile has exploded. I mean, I'm not even comparing to 20 years ago, but even the last few years, everyone wants to check his account once a day, even sometimes in the evening, many times an hour, to know if you can buy your last beer. It shows for us, and the numbers show like a 7-fold increase of all interaction with the bank, so making a transaction, but also checking your account. And on top of that, the online, the PSD2 is coming, and it's about exposing services from financial institution to third parties. So any software company would be able to use APIs from the bank to get information about the customer, to get information about the account and a list of transactions, for instance. So not only we would get all the customers checking their account, but also extra other vendors accessing our system. This would increase the load on our system on a huge amount. We have an integration layer based on TIBCO right now, and it gives a latency of 200 to 300 milliseconds. That's quite a lot. And all our attempts to scale up vertically, well, they failed. But let me talk a bit more about ING. Well, OK. The ING is present in many countries, but mainly in Europe. It's the main bank in the Netherlands, a fourth bank in Belgium. We have about 40 million customers around the world, and 10 million of them are primary customers, meaning that they count on us to do their primary banking. They have, for instance, loans at ING. Oh, there's something wrong with the... So our strategy, OK, there's something wrong with the PowerPoint. Anyways, so our motto is empowering people to stay a step ahead in life and in business. And for that, we want to be anytime, anywhere, meaning that customers should be able to access our services at any time from anywhere. And to do that, I'm going to focus on two of the differentiating experiences. Yeah, there's really something wrong with the slides there. Anyway, OK. Well, the number two actually was to be highlighted. Well, we need to develop analytic skills to understand our customers better. And also, we need to increase the pace of innovation and therefore do our digital transformation to serve our customers even better. So why did we choose in-memory platforms, amongst others, by the way? So they're supposed to be resilient, performant, scalable. We have, if you look at Ignite and GridGain, they have an open source part and also professional support, which is very important for us. As a bank, we need to be able to rely on a professional support when having a solution in production. They use Java. ING has bet a lot on Java. And, well, as I described, they're very promising. Now I'm going to go through different applications that are using in-memory computing in ING. I'll go through SEPA Direct Debit. It uses a lot the compute and the data grid of Ignite. Multi-bank customer reporting, also focusing on both parts. I'll go through the real-time gateway, which is really focusing on the compute part of it, not really the data part. Shielding, which is mostly on its side of the data part, and it's quite useful for us to get rid of those mainframes. And finally, I'll talk about a project that we have inside ING, which is GridGain as a service. For SEPA Direct Debit. So what's direct debit? For instance, as a customer, I can allow the electric company, for instance, I live in Belgium. Let's say I have a house in France. Before, if you want to be able to get your electricity bill paid, you had to open an account in France. But now with the SEPA Direct Debit, it's an EU law. You can have an account in Belgium and have this company, the electricity company, take money from your account. They have a mandate, and with this mandate, they can collect money on your account. So most of the time, the creditor, the one that collects money, is a big company. They send a lot of direct debit per day. Let's say a file with 50 million, sometimes, not 50 million, but let's say 10 million transactions, so that the money has to be collected from the different accounts of the customers. We have the different companies such as utility companies like internet, gas, electricity, but also card company that will withdraw money from your account. as ING, we need to be able to offer very aggressive cutoff times. So we need to be able to process those files very quickly so that the customers have the money on the account as fast as possible. It's very important for us and for them. We need to be able to offer information to the customers so that they can see what happened on their account very quickly. They need to have this information fast, and therefore we need to have all this processing be done in a very short time. And finally, as I mentioned, this PSD2 initiative pushes us to offer APIs to be able, so that other companies, so that software vendors can access this information as well. So for this, we chose to use Ignite and GridGain. We receive files that are in an ISO XML format through a Kafka bus, and then they have an XML parser which is on Ignite, which runs a compute task, will parse the file. It will store the file in an intermediate state cache where we can get all this information. Then, after that, another job is taken up, and it's going to validate all the information using the compute and distributed compute. Also using collocation, we can ensure that we have the compute being done at the right place, on the right server, so less data is exchanged between the nodes. Finally, after aggregation of data, we will put the data in a permanent cache where it can be queried by the different APIs. So using this cache and SQL, we can have a REST API that can query all information, like a customer can see all the debit that happened on his account, or provide this information to software vendors by PSD2. The multi-bank customer reporting project is about processing files that are coming from the payment engine. So the payment engine sends us file of all operations that happen on an account of a customer. We're talking about large corporations here. And so we need to gather all this information and be able to group them, to merge them, and be able to send a daily report to the customers. What we have right now is an application running on Java. It's running on WebSphere, 2 servers using Oracle database. It's using a very old framework, very complicated framework. That wasn't made for distributed computing to be able. So we have very complex application, complex routines, so that both servers can run at the same time. And this framework is not extensible. It's a very complex one. So pretty much, with every need that comes, we are really struggling. So we decided to move to in-memory platform. So the new version, what's important to understand is that the new version shouldn't impact the interacting environment. So the payment system or the reporting system shouldn't be impacted. So we put it in the middle of those systems. The connection via MQ goes through a Kafka bridge. And then we have this in-memory cluster where we process all the files. So first, they are parsed. Then they put in a store where a continuous query will check them and will process them and put them to the next state, and so on and so forth. So they will jump from state to state, jumping from cache to cache. And once they are merged, so all the statements are in a store, and we're going to check if all the statements are there, and we're going to look at if they correspond to each other and do a final merge saying, OK, that's the balance before the day, at the beginning of the day, and that's the balance at the end of the day. And we send this information forward to a reporting applications. This application, the users that are using this application are mostly internal staff to check that everything's fine, that the files are in the right state. But to be able to prevent the processing to be impacted by access from the customer, and also because the model is a bit different, we copy the data in a different cache, in a query cache, so that UI application can access this information without disturbing the existing. The real-time gateway has been introduced because of a new need that we have in Europe. It's about the instant payments initiative. Instant payment initiative states that now from a bank to another bank, so 2 different banks, the payment should take them less than 5 seconds. So if I send money to a colleague that has another bank, then he should see the money on his account within 5 seconds. To do that, Belgium has chosen to go through a software provider called STET that will connect all the banks together. So the round trip from an external bank to ING, for instance, should take them less than 5 seconds. As I mentioned, our payment engine is still running on mainframe. So we needed a component to connect the STET environment to our mainframes. It will transform this ISO format that we receive from the STET environment into COBOL format and vice versa. So for that, we also used in-memory computing. Here, we use a different flavor of it. So there's no huge data store because the message flow from one side to the other, and they're not stored in the compute grid. They're stored on one side or the other. They're stored in our payment engine, or they're stored outside, but not in our compute grid. So the payments are, so the files are parsed and moved from our payment engine to our state consumer. And here we use the distributed platform and the power of in-memory computing to be able to process many messages at the same time. We're talking about millions of transactions. And here, everything, so the 2 round trips have to be done in less than 5 seconds. Now, shielding. Shielding is very important for us because it's going to help us to get rid or to move out of those mainframes. Shielding is going to be a cache on top of the mainframe, the existing mainframe. So we're going to have a huge number of server nodes with a lot of data and a lot of caches to be able to offload offload the requests that are reaching our mainframes. Mainframes are very good at batch processing, but when it comes to a lot of parallel tasks, parallel requests, it's a bit more complex for the mainframes. So here we use our Ignite and a lot of data grid to be able to store all the information that the mainframe have. We put them in data, in memory, so that when a request comes in, it doesn't have to go to the mainframe. But if you want to have more information, I suggest you check this presentation from a colleague of mine, Lieven Merks. He did that 2 years or last year in Amsterdam in the in-memory computing summit in Europe. Last but not least, grid gain as a service. So as we see that grid gain and Ignite is taking a lot of momentum in ING, we want to be able to provide services that all our engineers will be able to use very quickly. Myself, I'm part of a team called Building Blocks. So my customers are engineers at ING, and we want to provide solutions, software, frameworks, libraries for our engineers at ING to use so that, it makes the journey faster and they can go to production faster. And among them, we use grid gain as a service. This talk I've presented in June in London, and the first part was not struck out because in the beginning, we were planning on offering a server node based on Docker, having all the libraries deployed. But we realized that actually our engineers didn't need that. Using Maven, they will bring all the grid gain dependency together, and they will deploy that as a jar on their node. So this is not used anymore. But still, we need to be able to provide to our engineers something to monitor their application, something to make sure that everything's running fine. And that's why we have the web console and encryption, all the ING standards being provided as a service. So they will be able to get a Docker image with all those software components so that for them, they will only focus on their software. All right. So what's the takeaway? First, it's very important to understand that in-memory computing is very different from our old 3-tier architecture with a database, an application server, potentially a UI. You have to think differently. You have to make your data model, your business a bit differently. And that takes still time to adapt. And IMC, or in-memory computing, is still new. It's hard to find good engineers on the market to be able to help us in developing those those software. It's very complex. We are still, as you can see, exploring different types of use cases. We have some places where actually we wouldn't need really in-memory computing, but we use it to learn about it, to be able to understand how it reacts, the shortcomings or the advantages that in-memory computing provides. And it's definitely an attractive technology. It provides a lot of potential. We see a lot of interesting patterns. And by the way, I'm going to do a short talk tomorrow about one of the patterns we're trying to develop using classless design. And so this is very important for us to look into this emerging technology because we need to be on the edge of the technology and on the edge of innovation. But yeah, in-memory computing is not a silver bullet, and it still has some issues. For instance, we tried at some point to have many different teams working on the same cluster, and that didn't work. Ignite, for instance, sends around the cache configuration to all the nodes. So if for instance, you have application that they rely on Oracle data store and an application that rely on a Cassandra data store, well, every node that connect to those applications, they will need to have the drivers corresponding because they will have to be able to deserialize the cache configuration. And if they don't have the right classes in the class path, it's going to fail. So this pushed us to have different clusters for different applications. We tried to do an orchestrator based on Ignite, and we failed miserably. It didn't work properly. We ended up having a very complex application, so we moved out of it. And finally, a lot of our services in shielding, for instance, are based on a service grid. And unfortunately, so far, the service grid, if you want to update a service, you need to take the whole grid down. And 24/7, the whole grid down doesn't go together. So this is something we are waiting that it's being improved. But so far, we're trying to stay away from the service grid. Right, that was all. Thanks for listening. And yeah, have a nice break and enjoy the talk.